So in the first two videos, we derived the product and quotient rules. And in this video, we're going to go ahead and use the product rule to find the derivative. So the product rule is sitting down here. The product rule simply says that if you want to find d dx, or the derivative of the product of two functions, we simply take the derivative of the first function times the second, plus the first function times the derivative of the second. And when we're working through and using the product rule in examples, we want to remember from the previous homework assignment that we developed a series of techniques, all of which you'll need to be able to use in addition to using the product rule. So we learned the power rule, we learned the derivative of a sum or difference of functions, the derivative of a constant multiple of a function, the derivative of a constant being 0, and the derivative of x being equal to 1. So these are all tools that you're expected to remember, memorize, and be able to use in addition to using the new technique, the product rule. So we have a function h of x that is the product of two functions. So we have an expression here with three terms times an expression or function here that has three terms. The directions indicate that we need to find the derivative of h. And we could find the derivative of h without using the product rule. We could actually multiply these two three-term expressions out. We have three terms here times three terms here. We would get 9 individual terms if we multiplied these two functions out. And then we could use these techniques here in this box to take the derivative of each of the individual 9 terms. So what the product rule is going to allow us to do is find the derivative of h without actually having to multiply the two expressions out. So to take the derivative of h, we know we need to take d dx, the derivative of the product, and the product of the two functions. We have 3x to the fifth minus 3x squared plus 3 times x minus the cube root of x squared plus 2 over x. So we need to take the derivative of the product, and applying the product rule says first take the derivative of the first function. So take d dx of the 3x to the fifth minus the 3x squared plus 3. And then once you've taken that derivative, multiply it by the second function, which is going to be this 3-term expression right here. So times x minus the cube root of the x squared plus the 2 over x. Then it says plus, add on to that, take the first function, and the first function is just this 3-term expression right here. So plus 3x to the fifth minus the 3x squared plus 3, and multiply that by the derivative d dx. Take the derivative of the second function, and the second function is just this 3-term expression right here. So x minus, and now I want to begin to rewrite this term and this term in a form that will let me apply the power rule to them. So I have this radical form here. I'm going to write it with a rational exponent. So the cube root of x squared is the same as x to the 2/3 power. Plus, I have 2 over x to the first power, so I'm going to rewrite it with the x in the numerator position by negating the exponent. And now I can step through and do what this is asking me to do. This is just take the derivative of this first 3-term expression. So here I have a constant multiple of x to the fifth. So the derivative of a constant multiple is just going to be the constant times the derivative. So it's going to be the 3 times the derivative of x to the fifth. And x to the fifth, we can find its derivative with the power rule, which says bring the exponent down into the coefficient position and decrease the exponent by 1 in the exponent position. So that's applying the power rule. Minus, here's a constant multiple of x squared, so it's going to be the constant times the derivative of x squared. Use the power rule to take the derivative of x squared. Pull the 2 down into the coefficient position on x. and decrease the 2 in the exponent position by 1, plus take the derivative of 3, but the derivative of 3 is just 0. And then that's times the second function, x minus the cube root of x squared plus the 2 over x. Plus, here's the first function, just rewrite it, 3x to the 5th minus 3x squared plus 3 times the derivative of this 3-term expression. The derivative of x is just 1, minus, here I have a term to which I can apply the power rule. I have x to the a form, so pull the exponent down into the coefficient position and subtract 1 from the exponent in the exponent position. So 2/3 minus 1 is negative 1/3, plus a constant multiple of a function will be the constant times the derivative of x to the negative first. I can take the derivative of x to the negative first by using the power rule again. So pull the negative 1 down into the coefficient position on the x and decrease this exponent by 1. So negative 1 minus 1 is negative 2. And I can clean things up just a little bit. 3 times 5 is 15. X to the 4th minus 6. X to the first is just x. Adding the 0, I don't need to worry about that. X minus the cube root of the x squared plus the 2 over x plus 3x to the 5th minus 3x squared plus 3 times 1 minus the 2/3 x to the negative 1/3. I think it's okay to leave the negative exponent. We have a 2 times a negative 1, so we're going to get minus 2 x to the negative 2. And again, I think it's okay to leave the negative exponent. So the final question here, I'm going to say this is good. How much simplifying do you need to do? That's a key question. So when we're working on things, anytime we have clear and obvious simplifications, either algebraic or arithmetic simplifications, we want to do them. So if I have the square root of 49, I need to write it as 7. If I have the square root of 12, I need to simplify it to 2 times the square root of 3. If I have an x squared plus x squared, I need to simplify it to 2x squared. If I have x squared times x, I need to write it as x cubed. So clear, obvious arithmetic and algebraic simplifications, we need to do those. Here, when I look at what I have, there's no clear, obvious, immediate simplifications to do. And usually you're going to want to find the derivative to do something with it. For example, finding the slope of a tangent line. And if you do that, then you're just going to need to be plugging in a value for x anyway. So you might as well leave it like this. The only way we could do anything additional to this would be maybe to find common denominator within the parentheses, common denominator within the parentheses. But again, no real reason to do that. We could multiply these expressions out, and that would give us 2 times, here's 3 terms here, plus 3 terms times 3 terms, so 3 times 3. So we'd wind up with 6 plus 9 is 15 terms sitting there, and then we would need to look to combine like terms. And again, that would be so much work that it would defeat the purpose of using the product rule in this case to find the derivative. If we were going to multiply everything out and then simplify like terms, we might as well have multiplied everything out to begin with. So this is one where I think the spirit of this problem is to go ahead and leave it like this. Again, there's a little bit of judgment call that goes into when and how much to simplify. Again, if it's clear and obvious, do it. If it's clearly clunky to try to do it, then we probably don't need to simplify.